So I'm gonna try to give a brief mission overview. So I'm Nathan Kurtz. I'm the ICESat-2 deputy project scientist, but also one of the co-leads for the CICE collaboration team, as Joe mentioned. So for those of you who aren't familiar, just briefly, ICESat-2, it's a laser altimeter. It's a single laser pulse that's split into 6 beams. There's a strong and weak beams, so pairs along the surface. The strong and the weak beams are separated by 90 meters, whereas the beam pairs are separated by about 3 kilometers. And so we're taking measurements 10,000 times a second as the satellite is orbiting the Earth. And we essentially cover the Earth with our repeat tracks every 91 days. And so the current status, we've been transmitting laser light since October 1st, 2018. We're closing in on nearly 1 trillion laser pulses at the moment. And so we have an 11-meter footprint, and again, 70 meters a long track in between laser shots. And so ICESat-2 is very healthy. All our performance metrics are nominal, and we're operating within requirements for ICESat-2. In terms of the data products, the primary data product that we use for altimetry would be ATLO3. These are just each photon is geolocated, giving a latitude, longitude, elevation. And then these can flow into the land and sea ice products. Also, we do have atmospheric products that flow into these as well. But primarily on the land ice side, it would be ATLO6, giving you the land ice height at 40-meter segments. And then there are various time series and gridded products that are being produced and worked on. And same for sea ice. We have sea ice elevation retrievals, aggregating 150 photons, and then converting that to sea ice freeboard. So at a bit of a variable length scale, and then these go into our traditional gridded products for sea ice freeboard and as sea surface height. All the data are publicly available. They've been available since late May 2019. So these are, again, at NSIDC. We have almost 4,000 unique users to date for 14 available products and over 17 million files served. And so again, just different products that we do have for different disciplines. But again, the sea ice and land ice ones are probably most relevant for people here on the call. And then just a few summaries of some of the main results from ICESat-2. There's no way I can cover everything. There's been a lot of really good studies of ICESat-2. One of the main goals, especially for ice sheets, was to measure elevation change and connect that back to ICESat. And this was a paper in Science led by Ben Smith, but a number of people on this call and also involved with IARPIC involved in that study as well. But again, quantifying the amount of ice loss from Antarctica and Greenland, connecting this back to ICESat. On the sea ice side, again, ICESat-2 is adding that third dimension of freeboard. And so freeboard data products led by Ron Kwok and now taken up by Alec Petty are being produced. And so in addition to freeboard, Alec has led the way using snow model data to convert the freeboard to thickness, and again, providing data products and publications on those. And then another slide, just briefly, for some new applications that we're looking to spin up with ICESat-2. We're looking at a very low latency, 3 to 5 day latency product called QuickLooks. And there's been a lot of interest in these, especially on the sea ice side. And this is just a result for a paper now published in the cryosphere. Sinead Farrell made this slide showing how ICESat-2 can be useful for quantifying the degree of ridging and how this really could benefit ice services if we were to have this rapid release product. And so We're aiming to have that done by the end of this year and then released publicly. So ICESat-2 is very healthy. Instrument is operating very well, looks very stable. We have our end of prime mission and then looking to extend the mission proposal in January 2022. At that time, we're working to make sure that in reporting on whether we're meeting our mission requirements for both the ice sheet elevation and sea ice freeboard products. We do have various releases of the data products, the latest one being release 5, and looking to come out around the end of November of this year. And again, as I mentioned, these 3 to 5 latency quick look products for atmosphere and sea ice, and hoping to have those out by the end of 2021. And so
maybe I'd better get off it. Rachel's ready.
Sorry. All right, thank you. Don't know if we want to take any quick questions or if we need to move on to the next speakers.
Nathan, I suggest maybe any questions get posed to you in the chat, just so we can keep rolling. What do you say? Okay, great.
Yes.
Okay, great. So let's move on to the next presentation from Tyler.
All right. So I'm Tyler. I am a senior research scientist at the University of Washington, and this is kind of going to be a high-level overview of work from the Land Ice Science team, which is the work of a lot of brilliant people, and we're putting out a lot of different products. So let's start by rewinding a bit. Pre-ICESat-2, NASA was collecting data as part of NASA Operation Icebridge, which was an airborne campaign between the original ICESat mission and ICESat-2. Icebridge has a long legacy going back to the Arctic ice mapping and Parker campaigns. And these plots show kind of the airborne data that was collected over a time period that was over 20 years. And really what you can see is like NASA collected a lot of data as part of these airborne campaigns. And what you can see with these subplots is what ICESat-2 can provide is a very high data density. And as Nathan said, this is repeated every 91 days. So this is stuff that you can't just do with an airborne mission. So Icebridge was incredible, and it gave us all this great data and all these great science results. But what ICESat-2 can provide is giving this in a repeatable sense every 91 days. And so prior to me working with ICESat-2, I was doing what a lot of people were doing. I was taking Icebridge data and I was calculating elevation change rates. And so what these maps are, these are seasonal elevation change from Operation Icebridge over years where we had 2 campaigns, which was a phenomenal effort to put out 2 airborne campaigns, one in the spring, one in the fall, so that we could get the summer melt season and we could see what accumulation did in the winter. And how this worked with Icebridge was that you had the scanning geometry. So both of the laser altimeters that Icebridge flew, the airborne topographic mapper, ATM, and the land vegetation ice sensor, Elvis, had a scanning pattern. So ATM was a conical scanner. It kind of did these repeated spirals. And so the importance there was that you did not have to fly an exact repeat of last year's flight line in order to calculate elevation change. You could get close, and because you have the scanning pattern, you could calculate at that time what the long track and the cross track slope was. The original ICESat mission was what we called a nadir profiling laser altimeter. It had a single beam, and it measured in what would be like the shadow of the satellite. And kind of what this plot shows is ice sheets and glaciers, they're complex. There's steep slopes, there's crevasses, there's things that are difficult to measure if you don't measure an exact repeat. And so one of the deficiencies from the original ICESat mission was that if you didn't have precise pointing and you did not measure spot for spot, it was really hard to do a long track. So you had to group a bunch of years of data together to get elevation change. And that took a lot of effort. So how do you get something similar to scanning, which we have from these LiDAR, airborne LiDARs, to a spaceborne instrument? And that's something that Nathan brought up, is that you split up the beams. And so ICESat-2 has 6 beams. They're grouped into 3 beam pairs, and the beam pairs are separated. For a given beam pair, the 2 lasers are separated by 90 meters. And so you don't need to get exact. As long as it's within 45 meters pointing, you can do elevation change. You can get the along track and the across track slope simultaneously, and so you can measure through time. And that's basically what we're doing to get elevation change with ICESat-2, is that we can take these along track and cross track slope information, group them together to calculate an elevation change rate through time. This is what we're providing with ATL11. Where you have every cycle where there's precise pointing grouped together, and you can difference them directly and calculate what the elevation change rate was. So all that work that I once did to try and get these elevation change rates from airborne and from the original ICESat mission, that data is kind of just provided for us. Nearly Pan-Arctic. The bottom left plot shows in yellow where there's a lot of repeats. And the reason that it deviates over the land is that the land mission requirements are different from the land ice mission requirements. For land, we're trying to get as much coverage as possible to have a global vegetation measurement, so they're doing some off-pointing. Whereas over land ice, we really want the repeats. So we're trying to hit the same track every single time, every 91 days. And so while it's not complete Arctic coverage, we have a lot of the Arctic coverage in this repeat mode. And from these repeat measurements through time, we can make some assumptions and group them together with some strengths to calculate what the gridded maps would be. So this is an update from Ben showing the gridded land ice change. And the rightmost plot is what we get from ICESat-2. And this is going to be another product that is going to be put out, is the land ice gridded product from ICESat-2 from 2018. And that product will be out pretty soon. And so having all this great wealth of data means that you get to, as a scientist, start thinking about the process level change. Ice sheets and glaciers change elevation for a number of different processes, whether it's stuff at the surface from accumulation to melt, to changes in ice dynamics. And so you as a scientist get to start focusing now, as you have all this great data, all these great products, to start looking at the elevation change in this way. And so this is work that I'm doing with Ben. This is a plot from a paper that we're trying to put out soon, using ICESat-2 ATL11 measurements as a metric and a baseline to evaluate models. So these are surface mass balance and firm models from MAR and the Goddard Space Flight Center firm densification model. And so what we can kind of see is, even at like a quarterly 91-day difference, we have a way of seeing how well these models are doing from this spaceborne instrument, and it's really quite incredible. And so, kind of to sum up, we have ICESat-2 now. And so as a scientist, you get to focus on the science. There are different products for different purposes, from ATL03, the geolocated photon product, where you have a time, lat, lon, and elevation for every photon within a telemetry band that returns to the satellite. And that right now is the best place to look if you're trying to measure melt ponds or crevasses or very interesting things on the ice sheet that might not work at some of the higher level products. ATL06, like Nathan said, that's kind of the base level land ice product. That takes all the photon information within overlapping 40-meter segments and gives us elevation with slope information. ATL11 is something that came out later, and it is where we group all the long track and cross track information. You can do slices through time very simply to look at all sorts of different processes, from surface mass balance to tides to anything that could change the elevation on the ice sheet. And then there's the new products coming out soon, the gridded elevation change products and the gridded DEM. Great thing about ICESat-2 is from headquarters mandated down is that we are working in open science framework. So ATL 11, 14, and 15 are all developed in the open. They're in Python. You can go to the GitHub pages of Ben and Suzanne and myself, and you can just kind of look and see what we're doing to develop these products. And then a really cool product that's really kind of that myself and Ben are on, along with collaborators at Goddard Space Flight Center and here at UW, is Slide Rule, where you can get to design the product yourself. So if you want an ATL06-like product, but it's like 40 meters, way too big. I want 20 meters. You can set that. And so you can get to design the product how you see fit, and investigate processes that might not work at a 40-meter segment. So if you're looking at crevasses, maybe you could use Slide Rule and do this stuff in the cloud. And again, we're working in as much as an open science framework as possible. We're working across the science team. There's open sharing on Slack of data and science results all the time. So it's kind of working as what we want science to be going forward of it in a very collaborative sense. And that's also why we're sharing data here and showing results here, so that we could share to the community and get more people involved. And with that, we can switch to Rachel.
Awesome. Thanks, Tyler. Before we proceed with Rachel, I think we've got time. Any quick points or questions of clarification for Tyler? I have one real quick, Tyler. Just be clear, the ATL, I think 14 and 15, those products aren't available yet, but they're coming. Is that correct?
They're coming. Yeah. So we're going through the final stages right now. Okay. And yeah, so we have some test products into NSIDC, and we're getting those finalized. So soon. Okay, wonderful.
Okay. Any other quick questions for Tyler? I'll check the chat. All right, great. Well, oh, I see one hand went. Alec, there we go. Alec, go forth.
Yeah, Tyler, I was just wondering if the land ice community have utilized the cryo to ice, increasing overlaps with the ICESat-2 mission for any improved understanding of ICESat-2 performance.
My answer is going to be probably. So cryo to ice is going to be phenomenal over sea ice, because you will be able to really kind of determine the snow on sea ice quite well, as the radar will penetrate and the laser altimeter will measure more of the surface. That same sort of thing will work over ice sheets, where we could use the penetration depths of ICESat-2 and the much less penetration of the green laser, and try and figure out what's happening at its surface. As far as I know, I'm not sure how much that has been investigated on the land ice side and community, but there's definitely potential of doing that science.
Cool, thanks.
All right, well, without further ado, Rachel, would you like to share your screen and get started?
I would, yeah. Let's. Is that? How's that looking?
Looks good.
Awesome. Thanks, Joe. And thanks as well, Nathan and Tyler, for giving such good summaries of ICESat-2, because it means I can just jump straight in to talking about the sea ice. As Joe already said, I'm Rachel Tilling. I'm an assistant research scientist at the University of Maryland and NASA Goddard. And my work now primarily focuses on sea ice in the Arctic from ICESat-2, and a lot of that has been really honing in on melt ponds on Arctic summer sea ice, because historically satellite altimeters, especially radars, have struggled to estimate sea ice thickness in summer because the melting snow or the water on the melting snow appears very similar and is highly reflective, just like the leads between the sea ice surfaces. So you can't separate those surfaces, you can't get an accurate estimate of sea ice thickness. But this really fine resolution that we have now from the ICESat-2 laser system means we can start to detect actual individual melt ponds on sea ice, from altimetry at least, for the first time. And this has very much been a group effort with a bunch of us at NASA Goddard, but also had to give a special shout out to Mia Vanderwilt, who did a summer internship with us and has carried on her great work since then on melt pond detection. Before I jump into summer sea ice, I just wanted to kind of summarize sea ice from ICESat-2 in general. So, as Nathan already mentioned, the lowest level data product that you're likely to use for science applications over sea ice is ATL3, which is that geolocated photon cloud data. What that means is we're getting geolocated heights of individual photons relative to the ellipsoid, all of them time tagged from within this 11-ish meter footprint, with a vertical uncertainty of around 20 centimeters. But for the sea ice specific products, we've got something that's slightly coarser resolution. There's the ATL7 surface heights and ATL10 freeboard, which is derived from those surface heights. And each of those products is produced by aggregating 150 photons along track to lower the measurement precision to around 2 centimeters over flat surfaces at least. And that leads to a segment resolution of about 30 meters for the strong beams on average. And each of those individual kind of 30-meter segments will have a surface type that is associated with it. We now also have these higher level products, ATL20, ATL21, which are gridded freeboard and thickness estimates. And I believe they are available now on NSIDC, but Nathan can comment further on that. Okay, I know this looks kind of horrible, but I promise it's not. I really just wanted to include it because to understand the complications with ICESat-2 retrievals in summer, we first need to understand how surface type is classified for each of those ATL7 or ATL10 segments in winter, which is just what's shown here. And essentially the surface type classification is based on this decision tree. The first part of that decision tree just looks at the surface reflectance for a segment, which is what we get from photon rate. Photon rate is the number of signal photons returned for each pulse. That's usually around 10 or so for a snow-covered or a sea ice surface. But if we have a very, very low number of signal photons, we'll define it as cloud. And if not, we move on to look at our next kind of parameter, which is surface roughness, which we get just by fitting a Gaussian to photon heights within a segment. For each of those kind of reflectance and surface roughness combinations, we look at the background, which is just a proxy for the surface albedo. So the ICESat-2 detection system, it doesn't just detect return signal photons, it also detects background photons, mainly from the sun reflecting off snow and other highly reflective surfaces. And those high albedo surfaces become ice, lower albedo become lead. And when I put the word specular here, we're just referring to very highly reflective, almost mirror-like surfaces that appear like a mirror to the ICESat-2 laser system. And yeah, you really don't need to remember all this. It's just a takeaway that the surfaces are classified based on these 3 key criteria: the signal reflectance, the surface roughness, and the albedo of the surface. In short, the classification system, it works well. So this is just overplotting the ICESat-2 ATL7 surface type on Sentinel-2 imagery. And you can see that we're picking out even kind of those really narrow leads here. The other great benefit of this compared to, say, a radar system is you are detecting sea ice right up to the edge of these sea ice flows. With radar altimeters, they tend to struggle kind of this close to the edge of the sea ice flow because the leads are so highly reflective to the radar system that you'll get data dropout near there. So that's a really great benefit of ICESat-2. And Alec Petty led a paper that was out this year looking at surface classification from ICESat-2, focusing on those high-level sea ice products. So check that out if you want to know more and have a look at a lot more nice Sentinel-2 images as well. All right, that was sea ice from ICESat-2 in general, but now onto the bit that I think is the best bit, which is focusing on summer sea ice and looking a bit more about how the signals over sea ice behave in summer. All right, here's that decision tree again from a few slides ago, showing the ICESat-2 surface type classification in winter that, as we saw, does a good job, but the problem comes in summer, where the current classification scheme, all of these surfaces circled in red become ice or pond, lead or pond. Basically, anything except cloud could be classified as a melt pond in the ICESat-2 classification system. So although there are surface height estimates for summer from ICESat-2, they are likely to be less reliable because at the minute, they're not separating melt pond surfaces from other surface types, which is really why we're now putting a lot of effort into detecting and automating detection of melt ponds on sea ice from ICESat-2. And to understand ICESat-2 over melt ponds, we really have to take it back to ATL3, to the geolocated photon cloud data. This is an example that's very close to my heart. It's the first ever melt pond that I saw in ICESat-2 data way back, well, pretty far back, at the end of 2019 now. And when I first kind of saw the Sentinel-2 imagery with the track overlaid and the ATL3 cloud here, I was genuinely really excited. This is a pond in the Lincoln Sea. It's around 500 meters in length. And ICESat-2 is tracking to the top of the pond surface, but it's also tracking to the bottom of the pond as well, because the surface roughness, in this case at least, is just right for some penetration of the signal to occur. And coming from a more radar background, for an altimeter to be able to do that is just remarkable, because this is an instrument that's kind of 500 kilometers up, emitting billions of photons each pulse, yet it's able to detect individual photons from the bottom of a sea ice melt pond, which I think is just awesome. Not all of these will be signal photons or high confidence photons, but if you do plot everything up, you can see there's a clear pond signal in there. But with the ATL7 data, which we're plotting down here, which is that 150 photon aggregate, you do get a data dropout, which is probably because the surface finding algorithm, which assumes this Gaussian surface height distribution, fails in those cases. So if we want to know more about ponds, we really have to go back to the ATL3 data. The previous example was an instance where we found a pond in imagery and then found it in the ICESat-2 data, which is really cool. But what we want to be able to do is automate the detection of melt ponds and then verify it using imagery, so that eventually we don't need to rely on the imagery at all. And that's something that Mia has been working on during her summer internship with us at NASA Goddard. So she starts actually with the ATL3 data and calculates the signal to noise ratio of individual photons. And the algorithm we've been using was first developed by Jeff Lee and adapted for Python by Tyler. So thank you, Tyler, for that. It's been really, really useful. And also thanks to Jeff and Amy Gibbons too for all their help with kind of figuring out why we're seeing what we're seeing in that. Once we have these low SNR transects, which you might expect over ponds where signal penetration has occurred, we pick them out. And then to separate those from just kind of low signal to noise leads, Mia checks for bimodality to make sure that you are seeing those double surfaces. And as an extra bonus, she carries out surface fitting to both the surface and the bottom of the melt pond with an exponentially modified Gaussian. So we're then able to find both of those surfaces in the ICESat-2 ATL3 data and compare it with ATL7, which actually kind of tracks somewhere between the two surfaces most of the times with a much coarser resolution. And then just to verify, there's those two ponds in Sentinel-2 imagery, which gives us great confidence in Mia's automated method. Okay, this is the last pond slide now, I promise. And just to show that there's different ways that you have to detect melt ponds on sea ice. So all of those previous examples have been of nice big ponds, but what about when the surface gets a bit more messy and you have a bunch of smaller, higher reflective melt ponds? We've been using WorldView 3 imagery for that, which has this incredible resolution of around 46 centimeters. And this is just the WorldView image with ICESat-2 overplotted. That's the central beam, I believe, in the central Arctic Ocean. And it's here that you really start to see the benefit of ICESat-2 photon counting and the small footprint, because all photons are plotted here, with the dark green being the high confidence photons. And what you can do is use those to calculate the number of photons that are returned per pulse, which is just an estimate of the reflectivity of the surface. And these highly reflective surfaces just match up really nicely with the location of those small reflective melt ponds, which we then separate from drain ponds or leads by applying a relatively simple height filter. One of the issues, again, we're noticing is that in ATL7, some of these ponds are classified as lead, which will impact your sea ice freeboard estimates, and again goes to highlight the importance of being able to at least filter out these ponds from the higher level sea ice processing. Okay, and yeah, just to finish up, the current ICESat-2 sea ice products don't separate melt ponds from ice or ocean, but we can use individual photon heights, pulse level, kind of signal to noise ratio, or photon rates to begin to automate detection of melt ponds on the ice surface. But different algorithms are needed for different pond characteristics. So hopefully this has been enough to convince you that we need a two-pronged approach. One automation for larger, rougher ponds and another one for these smaller reflective ponds. And it's been a very promising step towards algorithm development of other melt pond parameters like melt pond fraction, melt pond depth, and also improving summer sea ice freeboard and thickness products. If you want to know more about high resolution sea ice topography from ICESat-2, those top two papers that were out last year, a really nice introduction to that. And as I mentioned, Alex's paper is a great intro to surface classification in the higher level sea ice products. And I'll finish there. Thank you.
Awesome. Thank you, Rachel. That was really cool to see those visuals, and yeah, very impressive with melt pond detection. Let's open the floor to questions. I've got one. I see Ellen has got her hand up. I'll let Ellen go forth.
Yeah, hi. Very cool presentation, Rachel. It's awesome to see another melt pond algorithm for detection of the surface and the bottom. And it was funny to see those two melt ponds that you showed in your example are also the two of the melt ponds that we showed in that second paper listed up there. I was wondering, do you have like an automated way to find melt ponds on the sea ice, or are you just like looking for ponds and then tracking them?
So Mia has been working to develop this automated algorithm. So we start by looking for these transects of low signal to noise, pick those out, and then check for bimodality of the surface, and anything that is bimodal is defined as a pond. And we're actually finding that I think even it was one granule, we found about 15 potential pond surfaces using that as automation, and then have been working to line that up with the imagery to verify that we are actually finding ponds. And so far, we're pretty confident that we're finding pond surfaces automatically now.
Okay, thanks.
All right, thanks, Ellen. If I could interject a question, just kind of trying to connect the scales between what Tyler was looking at and Rachel was looking at. You know, Tyler, you were often showing examples at scale of the whole ice sheet and the higher level products associated with that. In the end, you mentioned this thing that's under development called a slide rule to process the photon clouds on the cloud. And I thought, well, who in their right mind would want to go down to the photon level again if you're looking at all these large scales? And then, of course, Rachel offered the great example of why we would want to do that. And I guess so. Rachel, my question for you is like, how are you thinking about this slide rule? Are you planning on? You're obviously using the photon clouds themselves. Are you planning on using a tool like that, and how are you thinking about that?
I think for what I'm doing, it might be a bit tricky purely because I'm obsessed with literal individual photons. I think for especially those smaller examples that I showed of the 25-meter-ish ponds, you need to be able to count every single individual signal photon that's coming back to the detector. It would be awesome to scale it up, but at the minute I'm still so far down in the weeds that I don't have plans to do that, although hopefully at some point I could.
Okay, great. Well, once you show it works really well, then someone will want you to scale it up. Great. Any other questions for Tyler and Rachel? And I suppose I'll throw Nathan into the mix too. Relatively quiet on the
And
questions.
Joe, could I maybe just add to that? Yeah, I think, yeah, I agree with what Rachel said about the slide rule project. I think eventually the hope is that, as people want to make improvements to the products that are currently available, currently that the way to do that is to, contact us and, start a conversation. But I think slide rule offers this kind of more streamlined and automated approach to improve the official products we have out there. Initially for people just to work on the products and make changes and do science and play around with it, but eventually it would be, the great thing then is that something will be demonstrated within the framework that we're also using, so we could potentially implement changes that others are have shown and tested and implemented themselves. So yeah, the exciting there's exciting prospects down the line for that kind of more collaborative approach to product development, which is cool, but yeah, might be a while for that to really be fully implemented, but be fun to see how that goes.
Thanks, Alec. Olivia, you've got your hand up.
Yep, thanks, Joe. I have a question for Rachel, and maybe coming up with follow-up to Alec's comment just now. How far away are you from welcoming collaborations with, say, biologists who are going to want to ask questions about how melt pond changes are impacting primary productivity or under ice productivity? Is this now a good stage to be connecting with your research group, or would you still be focused on your algorithm development, and that's just a couple of years down the road before you're ready to start collaborating with biologists? Because clearly this is still a tool or a methodology that's over the heads of what most biologists would be using, but of very important interest in developing future research questions.
Yeah, definitely. I mean, we're already starting collaborating with biologists. I'm always open to any kind of collaboration, and we're lucky enough that we have a couple of projects on the ICESat-2 science team side, people who are also looking at the sea ice products in the Arctic Ocean. I've been kind of working with them to find the locations of ponds and also the locations of very wide leads, so they can start looking at primary productivity in those areas using, again, the kind of very fine resolution ATL3 data from ICESat-2. So it's something we've already started doing. It's something I'm really excited about, and definitely open to talking to anyone else about that as well.
Cool. Good question. Good answer. Any other questions from the audience? Jessica's got one. Jessica, do you want to speak a little more to your question? It's in the chat here.
Sure. I was just wondering if Rachel had a chance to try her algorithm on land ice, or I should say Mia's algorithm on land ice, since obviously detection of melt ponds is of great interest there as well.
I haven't, but mainly because I know there's a lot of people who are working on that over land ice who will be doing a much better job than I think I would be able to do with my sea ice knowledge. So, there's definitely people working on it.
And to follow on that, the algorithm that Jeff Lee put together of it's called YAPC. It's a way of classifying photons, and so we're looking to using that sort of technology and that sort of algorithm on the land ice side, and then maybe doing something similar of looking for multiple modes and segment to try and get melt ponds that way. But right now, the land ice ATL06 doesn't, as Ben Smith likes to say, it breaks the warranty when we look at melt ponds. But we're looking into folding that in and using YAPC and all this cool new science to get maybe that in those products as well.
Tyler, do you think melt ponds create any kind of ambiguity in the large scale products for DHDT on land ice? Or any substantial ambiguity?
So we try to, when it comes to like doing like the graded products, we try to mask them out, just as the land ice algorithm doesn't do that well. Sometimes it gets the surface, sometimes it gets the bottom, sometimes it's in between. So we try to get rid of them at this point. There's a number of like quality flags, and oftentimes the melt ponds break the quality, like they just like, this is a bad point because it's seeing two surfaces, and so the algorithm's like, we don't want to use this. But in any part where we can't, like if there's a melt pond that somehow passed the quality flags and somehow passed detection, then maybe, but we're trying to get rid of them for now.
Okay, great, thanks. Any last questions for Rachel and Tyler and Nathan? Going once, going twice. Oh, whoa. Okay. Oh, that's not a question. It's more of a comment.
Sorry. Yeah, ignore that, Joe.
From Alan. Okay, great. Well, thanks everyone for joining. Well attended and much appreciated. Hopefully you learned something. I certainly did. And we'll be back for more ICESat-2 and adding on Grace follow-on next month on the Glaciers side. Olivia, Nathan, do you want to advertise the next Sea Ice collaboration team meeting?
We would if we had a plan. So just please keep a hold of your emails and we'll keep you informed with our next upcoming meeting plans.
Okay, great. Well, with that, thank you everyone for attending. Thank you, Rachel, Tyler, and Nathan for speaking, Meredith for organizing us, and to my co-leads for helping make it all happen. And we'll see you again next time. Bye-bye, everyone.
Thanks, everyone.